real treasures of having been an academic is to watch and in some cases help young people as they develop their careers professionally. And I've been very fortunate. I've had a good crew of students at MIT, and none of them means more to me than the fellow who's going to speak today. As I mentioned, Noam was a postdoc at MIT around the year 2000. He joined the faculty at Tel Aviv University, rose through the ranks very quickly. As his career developed, he's now the dean of engineering at the university. Noam, it's a very special day for me to have you join us here in Winchester, and I'm glad to see you. I'm glad to know you're well and safe, and we're looking forward to your presentation. So I'm going to turn the floor over to you. Noam will talk about additive manufacturing today, and I'm sure we're going to find it interesting. Noam, welcome.
Thank you very much, Ron, for the beautiful introduction. Do you see the screen?
Yeah, yes, perfect.
Okay. So today I will give you a snapshot about additive manufacturing. We focus on directed energy deposition. Actually, my journey in this area started at MIT during my postdoc, and I will show you a slide from that time in a period. So thank you for inviting me, Ron. At Tel Aviv University, I founded a new center for additive manufacturing based upon the DAD. The major funding came actually from the US dollar support of Israel, Optomet machine made in the US, and a large furnace. And now I'm also founding the Center for Advanced Manufacturing in India in a private university. So in recent years, I'm again into the additive after some break. So if we look over the history about the Industrial Revolution, so people said that now that we are currently in the fourth Industrial Revolution and additive manufacturing has an important role there. So think about history. In the first Industrial Revolution, used water and steam power to mechanize production. In 1764, the power of steam was discovered, and inventions such as the steam engine and the powered loom gradually led to the development of the industrial factory of the 19th century, where precision machine tools and the replaceable parts allowed greater efficiency and less waste. The second industrial revolution is generally dated between 1850 and 1914, up to the start of the First World War. That revolution used electric power to create mass production. Steel is often cited as the first of several new areas for industrial mass production, and we can go back to 1860s, where Sir Henry Bessemer invented a new furnace which would convert molten pig iron into steel in large quantities. The factory at that period was based on cracking out zillions of identical products. And we all know well, Ford famous said that car buyers could have any color they like as long as it was black. The third, so this is like the iron making or steel making. The first industrial revolution used already electronics and information technology to automate production. That the digital revolution started in the middle of the last century, and now the fourth industrial revolution is building on the third. It is characterized by a fusion of technologies that is blurring the lines between the physical, digital, and biological spheres. Future factories will probably look like something like this. So this is obviously a trick. I took this photo when I was in Germany. So this is one of the largest manufacturers of AM machines. But in theory or in principle, this is how we should expect the future factories to look like. So the factory of the future will focus on mass customization. The cost of producing much smaller batches of a wider variety with each product tailored to precisely to each customer's whims is falling, which will facilitate this. If we look at the McKinsey report, the 12 disruptive technologies, you will see one of the 12, the one that I marked, the 3D printing. So is considered an important disruptive technology nowadays. Here you see some examples. So on the bottom left, you see GE engineers produce this model of jet engine using an advanced 3D printed technique called direct metal laser melting. This manufacturing method is producing a growing list of parts for numerous industries, making stronger components with less material waste that are impossible to create using traditional techniques. Bottom right, you can see a concept plane by Airbus to be made circa 2050 with a 3D printer. It includes a fuselage structure based on the lightweight skeletons of birds. If you look at the tree of additive manufacturing techniques, so the American Society for Testing and Materials, ASTM, classified powder bed fusion and directed energy deposition that are on the right-hand side methods to represent the key beam-based approaches for fabricating metals and alloys. The high thermal and rapid stress and rapid solidification can lead to detrimental residual stress and defects such as delamination and severe part distortion. In addition, the beam-based metal additive manufacturing systems are energy inefficient and suffer from the high cost of technology and operations, as well as constraints on speed, precision, and surface quality. And moreover, as you will see also later, it is quite challenging to process non-weldable metals through beam-based metal AM systems. And therefore, in parallel to the beam metal systems, we have on the left-hand side the beamless metal additive manufacturing techniques that are being deployed effectively to overcome the limitations of the beam-based systems that I mentioned. There are numerous technologies that are being developed. I was very happy to see in this paper, and that's why I use it, the electrochemical methods on the left-hand side, because as I will show you later, this is one of the processes that we have been developing in my own lab here. So this is again a photo that I took in one of my visits in Germany. On the top, you can see a part that was manufactured from aluminum. So you can see on the left-hand side the batch of aluminum that was required to produce or fabricate this part. On the right-hand side, you can see the waste, all of the chips by machining. And then on the bottom-hand side, not at the same magnification and more zoom in, you can see the equivalent part that was designed to make it printable by additive manufacturing. On the left-hand side, you can see the batch or the raw material, the powder that is needed for this specific part. And on the right-hand side, you can see the supports or the waste that were generated using this process. Again, they are not to the same scale, but basically, although aluminum is lighter, thanks to this design and the reduction in volume, the part at the bottom is actually lighter than the part at the top and has better specific mechanical properties. And here you can see some of, for instance, on the top, on the right, you can see a part that was printed one piece, no weldings here, no other joints, no riveting, etc. And at the bottom, you can see some of the benefits of additive manufacturing that are often claimed. One has to be a little bit careful with some of when claiming always all of them. So this is the photo of Emmanuel Zatz. Ron and others probably know him very well from MIT, mechanical engineering. So I feel privileged that while I was working with Ron at MIT, while this revolution was still at its early time, I was a member of this team. Ron actually suggested whether I would like to join this and do the corrosion, be responsible to the corrosion part. Later I started doing the additive itself as well. So what you can see on the left-hand side, this is a 13-year-old guy from the Boston area that was born with this defect. So, and on the right-hand side, you can see already the computer model of the skull exhibit, the computer reconstruction, sorry, of the defects that you can see using a CAD file. Typically, these kind of defects are filled by using casting. But as you know, titanium is difficult to cast. Typically, the minimum wall thickness is around 1 millimeter, still as it used in 2001, according to the Ashby materials selection book. And with additive manufacturing, in this case, binder jetting, in principle, you can, as a rule of thumb, the minimal thickness that you can get is 10 times the diameter of the powder. And since you can use very fine atomized powders nowadays, you can easily get much lower than the 1 millimeter and customize it per demand. So this was a collaboration at the time with people from Harvard, dental school, and others. So on the right-hand side, you can see the top part, you can see the principle of binder jetting. You spread the powder, and then you come with the print head, and you can use either organic or inorganic binders. And according to your file, you just drop the liquid or the binder in areas that you want them, and then you lower the build plate, and this way you build layer by layer the whole part. Later, in this case, either you do sintering or liquid metal infiltration in order to densify the material. You can see in the center, like the kind of the powder that we were using, titanium powder, and what you see on top of them, like are fine droplets, solidified droplets of silver. At the time, we, as others worldwide, thought that silver will be fantastic for antimicrobial behavior, but recent studies in recent years, as the clinical data started to come up, it's now questionable, and now there is a debate in the clinical literature whether, for instance, silver nanoparticles should be used at all. On the right bottom side, you can see some of our corrosion studies. I won't get into the details, but basically the corrosion behavior depends on the porosity of the printed part, and with the titanium silver, we could get corrosion behavior that was as good or slightly better than pure commercially pure titanium medical grade. And we can talk about the effect of silver on the hydrogen evolution reaction and so on, but I will not get into it now. When we think about the powder laser-based technologies, so the powder bed fusion is significant, or one of the major ones, if not the major. So this is schematics where you on the left-hand side. So you spread the powder and you come with energy source, in this case, laser. You heat locally the powder according to your file, and you lower the build platform, and this way you build the parts layer by layer. And on the right-hand side, you can see the sparklings from the interaction of the laser with the powder. Considering the pros and cons of the powder bed fusion process, so you have more design freedom and high geometric complexity. For instance, you can print cellular structures and undercuts. You can get finest details and surface roughness achievable with laser, compared to you can do the powder bed fusion either with laser or with electron beam. When you use electron beam, you do it in vacuum. So with laser, where we also use finer powders, you can get finer surface roughness compared to the powder bed fusion with electron beam, and also low residual, and on the other end, low residual stresses and the low level of porosity when you use the electron beam in vacuum. You can also do the plating and so on. By the way, when we talk the finest surface roughness, I will show you later that with electrochemical printing, you can get much better. Among the cons, you are limited in the size of the object, and the technology's jumps are not huge over the years. It is not trivial to change the materials and the design of the building chambers to adapt for the high temperatures and the aggressive environment. There are issues with the removal of the support. Sometimes it's complicated. The materials range is quite limited, in particular when you work with the electron beam melting technique in vacuum. There you are limited to vacuum compatible materials, for instance, and all the gassing and so on. And intercontamination that people sometimes ignore. Just to give you a sense, people usually don't talk about it, but in companies, usually commercially pure titanium and titanium 6-4 are not printed in the same machine. They will have different machines for each one of the two. And even when you change from titanium 6-4 grade 5 to titanium 6-4 extra low interstitial, it is not recommended because you already presumably have too many contaminants in your chamber. And then you can think about other cons. Composites and functionally graded materials are challenging to print compared to DED, for instance. AM on non-flat surfaces is not possible. Part repair and cladding are not possible, or at least in recent years, there are some tricks that people are trying, still extremely challenging and not really useful at the moment. With laser, you get high residual thermal stresses and porosity risk. And so on, you can see here. Also, one has to take into account that these small powders, when you work with reactive metals like aluminum and titanium, are explosive. And I'm aware of already of several incidents of explosions in factories that they were using the powder bed fusion with laser and small powders and reactive metals. Okay. So let's move to DED then. So the most famous technology in the DED arena is the Optomex lens. Optomex is placed in Albuquerque, New Mexico. The technology was developed originally by Sandia National Labs and then licensed to Optomex, who still markets it. This is the largest company in this sector. The process involves very high, very rapid cooling rates, note 1,000 to 5,000 degrees per second. It, of course, affects the thermal residual stresses, but also the mechanical behavior. I will touch it later. You can get very fine grain structures that may be much finer than the comparable wrought alloy. Therefore, for instance, when you do repair with DED, the repaired area sometimes have better mechanical properties than the parent part. Some of the companies, including Optomex, you can buy it with a glove box with inert atmosphere. Optomex allows you to get less than 10 ppm oxygen in the chamber. This is very important when you want to get high quality aluminum or titanium or magnesium parts, as we are using, for instance. Okay, so the process looks like this. You have on the left-hand side, you have the schematic illustration of the DED process. You have, in this case, powder feed system with coaxial particle injection setup. I didn't mention, but the DED you can do also with wire. The inset shows the interaction zone with a convergence of the laser beam and powder particles into the molten pool and under inert atmosphere, which is important. And the inert atmosphere in the chamber is more effective than using like a shroud, for instance, as we sometimes use in welding, for instance. Okay, this is non-equilibrium processing technique, also has to be recalled. If you look which parameters are important, so you can see here that there are variety of parameters that can affect the outcome. Some of them are related to the specification of the system, for instance, the maximum laser power, which type of laser, the laser spot size, and so on. Some of them are related to the feedstock, powder feedstock parameters, like for instance, powder size, powder shape. The flowability is very important. Typically in DED, for instance, length, it is recommended that the powder will be between 44 to 150 microns, and it has to be spherical. We usually use gas atomizing. And then on the right-hand side, you have the deposition variables that you can adjust on the machine during the setup. We usually use in my lab design of experiments, Taguchi-based techniques to identify the synergistic and the antigenic interaction between the different parameters and the effect on the microstructure and the properties, for instance, the density and the mechanical properties of the parts. Here you can see some schematics of the physical process. So you can see here on the left-hand side, the top one, the layer by layer structure, different orientation of the scans result in these different shapes that you see between layers. We have here thermal cycles that affect, of course, the microstructure and the resulting properties. We need to account for the porosity. Typically, you will have higher porosity at the interface between the building plate and the sample. But then, of course, you can also get significant porosity in the bulk material, depending on the parameters that you are using. So this is one of the challenges in general that one has to optimize. I will show you in a moment what happens in the molten pool when the powder hits it and there is interaction between the powder particles and the molten pool. So you have one of the nice things about additive manufacturing is that it really revolves now the field of physical metallurgy that was somewhat declining worldwide. Think about Colorado School of Mines and other schools worldwide. And suddenly the young kids or young students are very excited to do metallurgy just because this is part of additive manufacturing, which sounds sexy, but basically we are looking at similar phenomena that we are looking in casting or in welding or in other processes. So here you can see the interaction between the particles that hit the melt pool using the fast camera at the University of California, Irvine, with my colleagues, Professor Enrique Lavernia and Professor Julie Shonung and their group. They moved to Austin, Texas recently. So it is well established that two particle capture regimes are identified when the particle reaches the molten pool surface. One is the submergence regime, where you see there the penetrating particle, and the other one is the floating regime. When the molten pool liquid can wet the surface of the particle, and the particle has a relatively high initial velocity, the particle will penetrate easily into the molten pool, resulting in the submergence regime. By contrast, if the particle and the molten pool liquid exhibit poor wetting, the particle tends to oscillate on the surface of the molten pool because of the surface tension force, therefore leading to a floating regime. And you also have back returned particles. So anyway, these particles will negatively affect the surface roughness. You will get rougher surfaces in those cases. So here you can see three examples of the use of directed energy deposition. On the left-hand side, you can see Bell helicopter exhaust that was fully printed from scratch. In the center, you can see repair of turbine blades. So for instance, there are some stages that are routinely repaired using this technology. This reached the highest TRL and MRL levels there. On the right-hand side, you can see hybrid additive manufacturing, like the machine that we have at Tel Aviv University, that you have both the additive and subtractive. So it combines both 3D printing or additive manufacturing and CNC milling, as you can see here. It is beneficial not for any application. It's really important. Sometimes it's cheaper to take the printed part out of the machine and move it to your machine shop. But there are certain applications where the hybrid AM is very valuable. If you want to, I can elaborate later, give you some examples. So looking at the pros and cons, so I was invited to serve on the ASTM committee that prepared this ASTM standard, or now also ISO standard for design for DED. And I asked the committee there to include in the standard, which is not always done, the pros and cons of this technology. And the reason it was that it was important for me to get some kind of support from experts in the field, that what I present to students at the conferences, they all agree with. So basically, if I compare to powder bed fusion, the DED has a larger materials range. You will see a table later. You can print multi-materials, this is a great advantage from composites, functionally graded materials. In the same machine, using multiple nozzles. For instance, at Tel Aviv University, I have 4 different nozzles, so I can print simultaneously 4 different materials. They are typically denser and mechanically stronger compared to powder bed fusion. Typically, there are, of course, some special cases where it doesn't happen. You can tailor the mechanical and material properties locally. You can do either full parts or coatings or repair in a single machine. Note the fast build speeds. You will see very large parts that are being printed using the DED. I mentioned here 2 kilowatt laser simply because this is the laser that I have at Tel Aviv, IPG fiber laser. In my case, there are some inventions there or new technologies there that are relevant. I can touch it later. You can print on non-horizontal surfaces. For instance, you saw the blades. You use larger powders in DED with laser compared to powder bed fusion with laser, which means that it's safer and it's cheaper. If you use wire in a vacuum atmosphere, so NASA is printing in zero gravity environment, and they have also modification that they did in-house. And for some things, the technology is fairly mature. For instance, all of the Abrams tanks are being routinely repaired with this technology. I showed you I gave you the example of turbine blades. I will be traveling to the United States next year in order to actually bring to Israel the know-how of turbine blade repair. I will be traveling to Hoffman company that is working with Optomate, and they are actually doing this 24/7. If we look at the cons of the DED, so shrinkage, residual stress, deformation, lower dimensional resolution compared to powder bed fusion with laser. So there are more complementary technologies. That's how we should regard them, and not as competing technologies. Each one of them is more powerful for different applications. So if you want quick manufacturing of large parts, near net shape, and you don't care about doing like final polishing, for instance, then you would go with DED. Or if you want multi-materials, on the other hand, if you need very fine cellular structures, cages for orthopedics or stents and so on, you will go with powder bed fusion. Okay, and you can see, I'll skip this. You could see this. So just to give you an example from the States, so they call it Mobile Parts Hospital. Last time I tried to log into the website, I couldn't, it was not operative anymore. But this idea in the States was to install this kind of printers on this vehicle carried chamber, and you can actually go to the field and do repair of parts actually in the field. You have, of course, some other technologies there. And here, this is the scale of TRL 129 and the MRL up to 10. So for some applications and for some materials, the technology and the materials and the applications got TRL 9 and MRL 10 already like 10 to 15 years ago. Some standards are already there. Just to give you a snapshot on some of them, there are, of course, more for the powders, but also for the design and so on. From one of our reviews, a list of some of the materials that have been successfully printed with DED. So you can see a broad spectrum from carbon steels to functionally graded materials, multi-layer composites, high entropy alloys, shape memory alloys, and so on. So you can see some examples on the left-hand side. You can see the kind of noses that you get typically with DED, and you will need to remove them for most applications with polishing. On the other end, on the right-hand side, you can see US Air Force data. So this is for titanium 64. You can see the difference in the SN curves or the dynamic mechanical properties between the cast material, the cast with what isostatic press treatment, the rotor yield, and then you can see the data for the DED. So you can see that in this case, the dynamic properties that you get with the DED are better than the powder beds, the blue triangles that you see at the bottom, but also compared to the traditional rods or cast alloys. And at the bottom, you can see for stainless steel that typically the as received material with DED, you can get mechanical properties that satisfy already the ASTM or ISO standards in terms of static strength and elongation. Some further examples from a thesis already from 2007. This is titanium-based alloys with titanium boride precipitates. Look how nice the interface between the precipitates and the matrix. It's quite impressive. On the left, on the left top side, you can see functionally graded materials where you actually have in the whole project, not in this specific picture, 3 alloys: titanium 64 that gives you high resistance for creep, titanium 2223 for low cycle fatigue, and the gamma titanium aluminide intermetallic for creep resistance. So you can now combine different materials in one part to get, in this case, optimized mechanical properties, okay? So this is titanium 22 aluminum 23 niobium. At the bottom, you can see from another thesis, the processing of DCIP, dual continuous immersed phases. This is a kind of composite where the matrix and the reinforcement ratio is approximately 50-50. And here what they did, they used mechanical design simulation to predict the mechanical properties that one will obtain with different orientations of the two materials, and then they quickly went to the lab and printed them. At the bottom left-hand side, you see an example of alumina, small parts. It's challenging to print large ceramic particles. Here you can see some examples. I mentioned the repair, so you can see the Chinook helicopter. This is already qualified US Army. It's not for several years already. And the T-700 stage bliss. So these are already approved, qualified processes. They save money to the Army or to the Air Force or whoever uses them. On the right-hand side, you can see the top free form, the position of a metal matrix composite, and so on. Some more examples from our review. So you can see the size, the large size of parts that can be printed. In this case, a large aerospace component but then you can also see the other applications. And in E, for instance, this is functionally graded magnetic, non-magnetic bimetallic structure. Actually, I have with me an example of 420 stainless steel on one end, 18 Inconel alloy on the other end. And if I take a magnet, I can just travel and it will start from magnetic to non-magnetic. The reason that we kept this unpolished is just that you can see the difference in the two materials according to the color. Otherwise, if I would polish them, you would not be able to notice. If we are already showing examples, So this is a memory from my time at MIT. So this is Hagia Sophia in Istanbul. So this is with the binder jetting. You can maybe appreciate the fine features, and this is actually for Caroline, that you can do with binder jetting. This is from Stratasys, just to show that they can print all colors. And again for Caroline, this was also printed. And going to metal, so this is from Space IL, so this is aluminum that was printed and so on. Basically, you can print concrete, you can print food, you can print glass, etc. Of course, not with DED. Another application of DED is alloy design. It's a very powerful tool for alloy design. This is one of the reasons that I brought it to the university. You can combine machine learning algorithms, high throughput design or computation tools with molecular dynamics as well, and so on, and then rapidly prints a large batch of samples in one shoot with modified chemistries or printing parameters and so on, and then optimize the materials. So there are some, Enrique Lavernia, for instance, he has a very nice invention related to this with the development of new magnetic materials. We are now working on high entropy alloys in this case and some other materials. So this is an example of repair of a broken gear. So you can see the different stages from the damaged tooth to filling of the missing part, and then after how it looks after machining. Again, this is already a part that is qualified for the company. Some other examples, so you can see on the left-hand side what we call hybrid manufacturing. So what this part, what they say hybrid in this case, that they are actually using the base. The base is made of stainless steel, and they are just adding locally the features by printing. The bottom part was manufactured by machining. So this, sometimes people use this the term hybrid, not to confuse with hybrid when we combine additive with subtractive. The Bell helicopter you saw earlier, so this is a qualified part. And then on the right-hand side, you can see the bioceramic coating calcium phosphate that was processed by DED. The reason that I put it, because we have been working on electrochemical deposition of calcium phosphates, and actually we are already after a scale-up process and implantation in humans. I'm a chief scientist of a company in Hungary, in Budapest, and now we are already at the stage of getting the CE mark for marketing this. This at the time was the only application that I could get that is not confidential. So this is from Lockheed Martin. So this is the frame of a nanosatellite. Originally, it was manufactured from aluminum with welding. They adjusted it for additive manufacturing, printed it one piece, no welding here, from titanium 6-4. And again, the printed part is lighter than the original machine, the welded aluminum part, with better specific mechanical properties and so on. So this is how the machine of us looks like. This is actually our piece when I went to the acceptance test in Albuquerque, New Mexico. And the same kid is on the right-hand side already at Tel Aviv, where we are using it. So this is how it looks like. One of the projects that is currently under journal review that I like is self-healing. So the field of self-healing metal matrix composites is gaining a lot of interest in recent years. Still, it is in its infancy. It's not like polymer-based shape memory, self-healing polymers, okay? It's much more complicated because the diffusion rates are different. You need to deal with oxidation issues, and so on. So we, as a brilliant PhD student of mine, came with this idea after seeing the report of NASA where they were using the feasibility test with casting, with steel casting, and he said why they were working off, they were using orthotectic alloy. So he said, let's design something which will be generic for any aluminum alloy, and will take advantage of the DED machine. So to make things short, this is a aluminum-based matrix that we developed, aluminum 5000, with the group at UCI. We jointly patented it. Then we incorporated during printing. Next step was to incorporate low melting point particles, zinc aluminum, that are used also in casting. We had to develop in-house here at Tel Aviv the shell, which is a diffusion barrier and the thermal barrier to protect the zinc aluminum core during the printing. And the idea is that when you have cracking of the aluminum matrix, it will break some of these shells, and as well as shell memory alloy that is supposed to be eventually also printed. This is without the shape memory alloy. Therefore, we had to apply external force, compressive force. Eventually, we hope that the shape memory alloy will give it intrinsically. And then if we do thermal treatment at relatively low temperatures that are sufficient to melt this core, it will be driven by capillary forces and fill the crack. And if you also have compressive stress that narrows the gap of the crack, you can easily fill it. And just to show you what you can see here, this is the aluminum part. We made a total fracture, and this is the same part on the right-hand side after we did the compression in that atmosphere. And this is the macroscopic view of the cross-section, just to show you where you see the ellipse. That's where the original fracture was. So it's still, of course, not perfect, but at least it encourages us that there is feasibility. With Professor David Zeidman at Northwestern University, I have an ongoing project, NSF BSF project, on the resusceptibility of a special equivalent to 17.4 pH stainless steel that was developed by Questec, a company of Greg Olson that you know from MIT and Northwestern and so on. So they developed the equivalent, they call it 17.4 plus, that is supposed to have better mechanical properties than the Roth 17.4. So they developed it for powder-based fusion. I asked the company that synthesizes the powder to synthesize, especially for us, DED, for DED, larger powder. And we are studying the susceptibility of these materials to hydrogen as compared to the Roth alloy. This is, I mentioned that we are developing in my lab electrochemical printing. So this is not powder bed. So what you can see, this is copper. We started with copper simply because electrodeposition of copper is well known. So what you can see, self-supported columns, and the substrate here is a sheet of copper also that was polished down to 0.05 micron. Look the surface roughness, how the surface of the substrate looks compared to the surface of this pillar. There is absolutely no additive manufacturing technology to date that can give you such a fine surface roughness. Here you can see an array of pillars that we placed manually. And on the right-hand side, note that the very high aspect ratio without bending. So this is important, and also top view, just to show you that it is fully dense. We patented this, and here we are looking for a partner, probably industrial partner, to build a printer together. Just to touch some of the challenges in this last part. So some of the challenges that we need to deal with is the porosity, minimize the porosity. It could be, for instance, gas porosity. Based on CT analysis of the shape of the spheres, for instance, of the pores, one can, for instance, relate them to different origins of the porosity. We looked at electrofusion as well, and so on. So microcity is important. When you look at printing aluminum alloys, it was mentioned in one of the early slides that it's challenging in general in these technologies. So aluminum has high laser reflectivity. This means that on a low energy absorption in the powder, this means that in order to print aluminum, you need to increase the laser power and decrease the laser strength speed. But aluminum, when it is melt, also has high thermal conductivity, high thermal expansion coefficient, oxidation resistance, and poor powder flowability. Therefore, it is very challenging to print high-quality aluminum-based alloys. Companies have been focusing for years on aluminum silicon simply because it's easier to print them. But as we know, there are much more interesting alloys for real use, like aluminum 2024. There, the laser reflectivity from copper is also challenging. And therefore, in recent years, companies like Optomet are now allowing you to choose another laser with back reflection to protect the laser and allow you to work with reflective surfaces. Some other challenges, machine costs. It's still expensive if you need several of them in your company. The question, okay. I will respond later. I see some questions, okay. The size, as I mentioned, in particular with the powder bed fusion, it's quite difficult to increase in significant jumps. The size, the dimensions. We are looking for machine learning-based approaches to minimize process optimization requirements. We have to deal with post-processing challenges, including surface modification and characterization. I will stop in a few seconds, and I will take questions on this one. At the bottom, you can see two horizons in my lab. One, when we were working with zinc aluminum, so we have a problem because we were concerned about the low melting point of zinc. Okay, so we didn't want it to leak into the aluminum matrix. But zinc has very negative potential for, it's at the bottom. It's quite at the bottom of the EMF series, and therefore we didn't find any published process for electrodeposition on zinc. Okay, specifically zinc powders with the high surface area. So we had to do some surface functionalization to make the zinc powder, zinc-based powder, hydrophobic, and then develop in-house shell technologies, both metallic and non-metallic. So on the left-hand side, you can see cobalt phosphorus. So you can see the X-ray mapping just to see that we got a nice shell. You can see the bright field image on the left-hand side. And in the middle, you can see SEM images of another surface modification process that we developed in-house. In this case, alumina on top of the zinc aluminum. And you see at the top part, when we don't use this process and we put this powder in the furnace, you have this kind of agglomeration and spongy piece, a brittle piece that is formed. When we use this surface modification in-house, the same powder, the same, except the surface modification, of course, the same furnace, the same treatment, and you don't see this kind of agglomeration. And finally, before taking your questions here, taking a break, on the right-hand side, what you can see, sometimes we have samples that we don't want to start working with ASTM dot-bound samples for so many samples. So on the right-hand side, we are using the dynamic pulse echo technique, for instance, to measure the elastic constants of the material. We can construct the whole tensor of elastic constants, and then we combine it, of course, later with tensile tests to get the yield point, UTS, and so on. Just as a small note, we found out, and this is supported by a report from the National Physical Laboratory in the United Kingdom, that it is more accurate to measure to determine the Young's modulus, for instance, from this kind of dynamic tests as compared to the static tensile test, okay? There are many explanations I will not touch. Okay, so sorry, I'll take a break just to answer your questions. Yeah, so Avi?
Okay, first, Noam, I want to thank you for the presentation. When I first heard about printing a few years ago, it sounded like pure science fiction. So my congratulations to you and others who've turned this science fiction into science reality. I've got two questions. The first is, could this be extended into the organic domain? Could you make, for example, in the ultimate, could you make organs for the body, or could you get down to at the cellular level? And it may sound like science fiction again, but you're good at turning fiction into reality. So that's the first question. The second one is, since politics infuses into everything, has the war in the Middle East affected what you're doing in the laboratory and the functionality of where you work at the university?
Thanks. So regarding the first one, this is not my personal expertise. I'm not a polymers guy, but the answer is definitely yes. People have already you have bioprinters. People are printing from small tissues and even organs nowadays. You have at MIT and other places. And actually, let me see, that's the advantage that I'm in the office. If I can quickly track one moment, presentations into the size. Okay, so what I will do for a moment, let me.
Does that mean that somebody has a defective liver or kidney, you can actually take the cells from the organ and print him or her a new body part, a new kidney, a new liver?
So we are not there, you know, this is what people are imagining. It will take years if you ask me to get to this. But I will show you, just let me see. Where is it? So this is a presentation that I give to school kids, okay? So that's why it's in Hebrew, so I apologize. 7th grade, like my kids. So let me see. I want to just to see whether to make sure that I shared with you the full screen presentation. Yep. Okay. So do you see this now?
Yes. Yes.
Okay. So this is for kids. You saw this, you saw. I explained to them what is the difference between 2 dimensions and 3 dimensions. And then I will skip some of this. Let me see. Okay. So this is an example from what you asked. So for instance, at Tel Aviv University in Life Sciences, we have Professor Tal Dvir that has been working on printing hearts. So it's not that, or our tissue, I should say at this point, okay? So it was on TV, it was published worldwide. He's not the first one and not the only one globally. So it started with small samples, but here on the top one, you can see already during the printing of the art. By the way, I will already take advantage of this presentation. We are nowadays also talking about not just 3D printing, but 4D printing, where the 4th dimension is time. So, for instance, to make one moment, let me see. Oh, yeah. So yeah, the movie doesn't work now. So basically, if it worked, you would see the Eiffel Tower just straighten up. And let me just to show you something, if we are already. People are working, this is large. We have a company in Israel that prints very large parts like cars. This is like buildings, for instance, in Russia, but also elsewhere, and bridges in Europe that are already printed. So you can print concrete, some imagination about space. And let me see. Yeah, there was food there, but I will skip the food. And then I'll bet. So the bottom line, for a long answer for a short question, the bottom line is yes. I mean, people are working on this, Linda Griffith at MIT and others. So this is, of course, we are not, if you ask me, for instance, for skeletal or heart tissues, this is already done. I mean, even nowadays, even in soldiers, injured soldiers, and so on. I showed you the maxillofacial surgery part from the MIT time. So what was developed there at that MIT has become, all hospitals in Israel have this kind of 3D printers, and they are nowadays just printing this customized. And the idea is that since you can print customized per the defect, you take the CT or whatever, and you print per the defect of the specific patient, the success rate is higher, you know, and the availability and so on. So for hard tissues, it's more common. For soft tissues, it's more limited, but it's on the way. I'm optimistic, but for instance, it will take years until you really replace the whole heart that was printed, if you ask me, okay? The second question, yes, I mean, it obviously affects and the war affects us in terms, for instance, some of our foreign students from India and so on left, and now they are only now are they coming back. You know, you order things even using the Amazon. It takes more, even not for the, even for the house, not just for the lab. It takes more time for them nowadays, and so on. But on the other hand, we are taking advantage of our technological capabilities to support, you know, develop new technologies very quickly and so on. So yeah, that's the bottom line.
You know,
Thanks.
just to add one short comment here. Over the course of our discussions, we've talked about the Materials Genome Initiative, and there have been some comparison with the Human Genome Project. And there really is a comparison. In both cases, you're looking at the structure of materials, genetic materials on one hand and engineering materials on the other hand. But what we learn is that the structure of those materials, one processed by nature, one processed by human, by artificial means, the structure determines their properties and their performance. And so in what Noam is describing is it's kind of a natural consequence of all of this. We may not be there in terms of producing organs yet, but it is happening and it's moving in that direction. It just strikes me as being so interesting that there is this coincidence between processing engineering materials and processing human materials. There really is an interesting coincidence. Avi, did you have a follow-up?
No, let's let other people get into it. I have a lot
Good.
follow-up, but let's let others get in.
All right, thank you. Let's go to Jenny.
Okay, well, thanks for the presentation. Very interesting to me.
I've not finished. Almost done.
I have a number of questions, but I will try just a couple of them. First, a general question. We all know there's three types of materials, right? Polymers, organic, and metals and ceramics. And the metals always been for the last decade or more, metal additive manufacturing considered to be more challenging than the polymer organic based. So I just wonder, by using the DED technique, what's your comparison, your experience in the most more demanding areas, such as the variation, part-to-part variations, and also the post-processing requirements, all these parts. So in those areas, how do you see that by using DED? What kind of advantage you have observed? Then I have a couple specific questions. You talk about the zero gravity environment. So in zero gravity, I just wonder what you have observed or experienced in terms of control the porosity. So it will be additional challenge to minimize the porosity in the parts, and also about the surface tension. So since the surface tension is one parameter which control the final quality, so how you control the consistency of temperature distribution. When you make the bed in the fusion bed, so if your temperature distribution is not uniform, you may have a different surface tension, then you have a kind of different surface either appearance and even the final mechanical properties. So I just want all these areas, what your observations, your experience, if you can, enlighten us a little bit.
Thanks, Jenny. Good questions. So let's start with the polymers versus the metals. So as you rightly said, the polymers is much simpler. The machines are simpler, and so on. If you look at Stratasys, for instance, which I know very well, Stratasys, the main reason that a few years ago they got into financial problem was because strategically, when the company started, they focused on polymers. Now, the added value of using additive manufacturing for polymers is smaller than for metals because polymers are cheap. Manufacturing processes of polymers are often more simpler than those of metals. And then it took them some years to realize that this is a strategic mistake. And then a few years ago, probably already 7 years ago, something like this, Stratasys started getting, in addition, also to the market of working to the market of metals. Now, with the added value with metals can be larger, as I mentioned. With DD specifically, I would say quick and dirty. If you need to, and you saw some example of the rocket nozzles, for instance, from NASA and so on. So this is, if you think about that, you can the high deposition rate and with good mechanical properties and no weak interfaces due to welding or riveting and so on. So there you have added value, and it is already used. I mean, it's not even the missile that was recently launched in the US, one piece printed. So again, it's DED based most of this. So let's say I would see DD, I would see the benefit mainly in multi-materials, in functionally graded materials. By the way, joining metal ceramics, you can also have good benefit compared to the traditional techniques. The project that we are working now with the US Air Force, what we are doing, you would probably not be able to do with any other process. Not that we are done with there, we didn't finish this, but from the beginning it was clear that no traditional material or no traditional process will allow them to function as they in that specific application. So does this answer your question regarding the DD, the first question, or I forgot something? Did I answer fully the first part of your question? Because I didn't try it. So just to make sure that I didn't leave anything for the first part of the DD, I will refer to the NASA or the zero gravity in a moment. But does it cover what I answered? Covered your first question? You are on mute, Jenny.
Yes. Yeah. I was asking about the surface tension.
So with the NASA, so I've not done anything on zero gravity, and actually most of the work by NASA is not public domain, so I cannot really tell you anything. I mean, we put it in the standard just that it is understandable that the process that NASA published that you can print under zero gravity, but again with wire, not with powder and in vacuum. But I don't have any information, and I didn't really pay much attention to this because it's too far from what I'm doing here. So sorry, I can't really say much there.
That's fine. Thank you.
I'm sensitive to the time. We have about 10 minutes left, and Noam has not quite finished his presentation. And I
I'm
see
almost
two
done.
hands. So Noam,
let me answer the guys because
okay.
I have 2 or 3 more slides which I can jump. Let me 1, 2. Yeah, I have only 2 more slides.
Okay.
So I can answer
Well, why don't we do the fun? Why don't we take your slides first and then go to
Okay.
the questions? All right.
Okay, fine with
So
me.
hang on, Michael and Eddie, hang on just a sec.
Okay, so let me share screen again. Screen one. Okay, so you see this.
Yeah.
Okay, so reusability of metal powders or recycling is an issue, in particular when you already worked in the printer with multi-materials. With respect to corrosion, and Ron is a worldwide expert in this area. So there are some specific issues when you think about DD or additively manufactured materials with respect to corrosion behaviors. So typically they are more porous and less homogeneous and possibly contain high residual stresses than the road counterpart metals. If you were talking about cellular structures, so you already have inherent crevices that could be the initiation sites for crevice corrosion. Powder quality, for instance, if you have moisture absorption, you might have hydrogen embrittlement, for instance, and so on. I mean, the corrosion behavior will be dependent on the printing technology because the microstructure, as Ron mentioned earlier, is important, will affect the properties. The dependent on your printing conditions and so on, the orientation or texture and so on. So there are new challenges and new things to learn that require further study with respect to the corrosion behavior of additively manufactured materials compared to the wrought alloys. And we have been doing this, for instance, we focus on hydrogen with electron beam melted powder bed fusion. This is with the Israel Atomic Energy Commission, and also with directed energy deposition, for instance, with the David Zeidman. So just to show you from our published papers on the titanium 6-4, we always compare the road to the EBM. So when we started this project some years ago, my hypothesis was at the time that I expected the additively manufactured alloys to be more susceptible, not always, but in average, more susceptible to hydrogen damage than the wrought alloys. At the time, there was no publication about this and no report on this. So we started studying this systematically under electrochemical hydrogen charging, gaseous hydrogen charging, and the behavior is different. I won't touch it. So what you can see here from one of our papers, you can see the microstructure on the titanium 6-4, the wrought alloy on the left-hand side, the electron beam melted powder bed fusion on the right-hand side. Of course, the microstructures are different, but then you can see the microcrack that propagated in the absence of any external load, just during the hydrogenation. We got later further mechanical tests and others to support this. So the bottom line that we claim is that the hydrogen and the electron beam melted material, now we are studying the DED, we will see, but is definitely more susceptible to hydrogen under aqueous environments compared to the wrought alloy. And this is something that people have to pay attention, because it is fairly young area, not sufficiently studied if you compare to the traditional wrought alloys, and one has to be careful when starting to implement these materials about their corrosion resistance or environmental. Yeah, and this is the last one. So the top end side, these are with our former president of the university, Professor Joseph Klafter, and that's since the money for the printer came from the Department of Defense with the US dollar support. So you see here the lunch, the kickoff meeting that we had. As in the Army, they gave it the special code, so public domain, I won't tell you, and that's at the bottom. This is from the inaugural meeting at Tapar Institute of Engineering and Technology, when we signed the MOU for the foundation of a new Center of Excellence in the area of advanced manufacturing, with focus on additive manufacturing. So with this, this is from Israel Defense about this project. So with this, I thank you very much, and I would be more than happy to take any other question.
Right, we have a couple of hands up, so let's go to Eddie. There you go.
Yes, I don't think I can get any technical questions answered in the amount of time we have. So I'm just going to say some very brief things. Number one, I've got a FDM printer going right beside me, and I make all kinds of things with it, including household items for various people. I think the whole additive manufacturing thing in the home has now become a fantastic revolution, because I literally print parts for half the family whenever things break. The other point is that I believe that steam engines were actually used in pumping water out of mines in 17th century Britain. So the application of steam engines actually goes further back, at least in general use. The other thing is that I believe that whole rockets are now being 3D printed by, I think it's a company called Electron, which is printing 3D printing rockets completely. I don't know if you know anything about that, but I'd be interested to know if you do.
Sorry, I told you, I don't know them specifically, and the things that I know from the US Air Force, obviously, I cannot share. So I'm sorry for
Right.
this.
No, that's all right. I had a
I think
suspicion.
to add a dimension to what Eddie said, there's no doubt that additive manufacturing is transformative, and it's changing the shape of our manufacturing process, no doubt.
Yes.
But there are
I-
some
I-
issues. There are things we have to pay
Yeah.
attention to, Noam, as you pointed out, and but it is transformative. Eddie?
Yeah, I should just mention that I got introduced to 3D printing at EMC, who started printing parts that broke rather than to try and get parts from manufacturers and suppliers.
Yeah.
It was just, like hours instead of weeks waiting for parts to come. So it was an enormous change in our manufacturing processes and huge advantage. So there's all those aspects to this whole new technology.
Yep.
Sorry, Marco.
All right.
Thanks, Eddie. Thank
Michael,
you.
let's take your question.
Yes, thank you for your presentation. We have a fellow out here years back who was speculating that if he could print or deposit conductive branched antenna arrays onto a non-conductive substrate, also with diodes, he could capture sunlight directly by printing antennas that were a fraction of the length of sunlight, which would be in the 200 to 400 nanometer range. His challenge was to get that array printed in those days. And he was expecting he could get a 78% efficiency if he could capture sunlight directly through these types of antennas. Can DED print this?
DD, no, it doesn't have the resolution, but the reason that I'm smiling is because the electrochemical printing that I showed you. So if you look at our patent, so one of the applications is nano antenna and the high terahertz application and so on, and now also with some optical systems. So there, some of our potential partners are from that field, and actually we are now already, at the moment, we have a project with a guy, a professor from electrical engineering, where we are doing this kind of very local printing. I had a project with a company, Orbotech. They are the #1 in the world in the market for repair of ultra high resolution screens, for instance. And there the project was that they wanted to use a process like ours in order to locally form the bridges and repair the metallurgical defects in copper or and so on. So the bottom line, the answer to your question is definitely yes, but not with DD.
Mhm.
And people are also using, nano dimension, and we have people working in quantum optics and so on. So there is another technology that people are also using. So yeah, it's very interesting.
Thank you. Appreciate that.
No, I would like to bring our session to a close, but I just want to ask one short question before I do that. If you were to compare the energy demand required to produce a given component, whatever it may be, using additive manufacturing approach and using traditional manufacturing, would there be how much of a difference is there? Is additive manufacturing more or less energy conservative?
So sometimes it depends on the application and the material run. As I mentioned in one of the pros and cons, so it's still with DD and powder bed fusion, for instance, it's sometimes more energy consuming than some of the traditional one.
Yeah.
But they give you some functionality, for instance, for some applications, it's less important, if the US Air Force is interested in ultra high temperature ceramics or in general in hypersonic applications, then everything is negligible. I remember from your course at MIT, we discussed the issue of costs of the materials, and for supercritical water oxidation systems and the others or reactors that the US are using liners made of gold and so on. So okay, I would not do it in a civilian area, but for some defense. So the bottom line is that there are sometimes people tend to ignore it. That's why I said when they show the pros and cons, they don't always talk about everything, but sometimes it's more energy consuming than the traditional one. But you will save some other, the money you will reimburse, for instance, by saving labor costs, you will shortening the lead time, and you have some other savings. So the bottom line, if you look at the whole chain, the idea is that typically it has to be cheaper.
Yeah, good. Well, Noam, I want to thank you on behalf of all of us.
I think that Wayne was trying to ask something, if you allow him.
Yes,
This has
just
been
a
wonderful.
quick practical question.
Oh,
You,
go ahead.
the only thing that you mentioned about laser sources was that you have an IPG fiber laser. What are the requirements on your laser sources, and is that the only type that you have?
So at Tel Aviv, let me see, just that I send you. Okay, so first I sent you a link, my email address. So in general, you are more than welcome to contact me with any question that may arise afterwards as well. Regarding the lasers are very important. Years ago when I visited in Germany, and I was shocked to hear at the time that from one of these companies that give services, that the director told the audience in the conference that when one of my employees brings me a part that was printed by powder bed fusion, SLM company at the conference was, I'm able to recognize from which machine in our factory, and that's one thing. And then if he she comes half a year later and try to do exactly the same, not always they will get the same results. And I was shocked. The technology has developed since then, okay? But at the time, I remember that I was shocked, and I returned to Israel, and I started thinking, why? What would be the origin? And my conclusion at the time was that it is probably has to do mostly with the laser, okay? So for instance, when I started with Optomate, what I really wanted them to give me a top 8 energy distribution, okay? They could not at the time, so you get the distribution like radialite with the IPG fiber. But the IPG fiber, for instance, you have issue of back reflection from copper, aluminum, some other materials. And the results, the quality of the alloy is not optimized sometimes. So that's why in recent years, you can now buy like IR laser, like with back reflection protection and so on. And last comment, when I bought the machine from Optomate, I paid for it and I asked them to leave me to manufacture for me a second port for a laser. So if a laser company, either in Israel or abroad, would like to work with us to use this as an open platform for the development of new lasers, we can quite easily install a second laser. Of course, some adjustments in the software, maybe also in the hardware. And actually now I just submitted a research proposal where I asked, among others, money to buy a second laser for working with also 2 kilowatt, but will allow me to better work with some of the materials, okay? So the bottom line is yes, you can think about maybe working with another idea that I had years ago, femtosecond laser and others, but we can communicate if you are interested later via email. I don't think we have time now for this.
Great, thank you.
Thanks, Noam. I should have mentioned that Wayne is an electro-optics expert. No, so this question follows. Thanks, Wayne. Well, let me bring this to a close. I want to thank you, Noam, for a wonderful presentation, and I want to wish everyone a happy holiday season, but especially Noam, give my best regards to Billy and your kids, and stay safe and stay well.